really clearly, but it's the best I can do. Have you noticed that the textbook always draws the X and Y and Z axes with that orientation? And what you might not have paid attention to is that the X's go outwards in the same about the Y's, and then the Z, which is much more intuitive, goes up the way, right? Now, if you imagine that we have a function, f of xy, and it could be something like x squared plus y squared, right? Something like that. If you try to draw that shape, this is where it gets really hard for me. It looks a bit like an acorn, right? Like an upside down cup. And the function f of xy equals x squared plus y squared is another way of saying the z coordinate is the x squared plus the y squared. So you can imagine as the x and y's, whether they're positive or negative, get bigger, won't the z values become higher as well? So you get this cup-like shape. And so when we talk about this fella or that fella, we're really talking about only the surface of the shape, right? Not the inside of it, just the surface. And that's what most three-dimensional, and we call them three-dimensional because you have to draw them in 3D to see them, most three-dimensional functions look like. So imagine that you wanted to integrate this function over a rectangle. That's the notation that they use. It's called a double integral because there's two integral signs. There's the function you're going to integrate, and dx by dy is just representing some rectangle on the floor. So you can imagine the rectangle on the floor was that one there. And let's say that this rectangle went from -1 to 1 in the y's, and maybe it went from, probably 1, -1 to 1 on the x's. Then we would describe this double integral in a little bit more detail like that. Now the notation is that if you do dx first and you do dy second, then the limits of integration of the x's go here, and then the limit of the integration of the y's go here. So just to put emphasis on it, the dx's go first and the dy's go second. Now in this particular example, since the x's and y's are the same values, you can't really tell that that's what's happening. But I think in my next question, I'll choose a shape that has different values. So now we have to figure out, how do you do integration when there's more than one variable? We know how to differentiate when there's more than one variable, right? Partial derivatives. We know how to do that. What we don't know yet is how to integrate. If the world was fair and math made sense, what would be the natural way of doing just this single integral that I'm showing with the dotted box around it? How do you think you could integrate something like this with respect to x?
Carry y through like a coefficient?
Yeah, treat y like a constant. In other words, remember when we did partial differentiation with respect to x, you differentiate with respect to x and every other variable is counted as a constant, right? So let's see what that looks like. The box is not really here, but I'm just doing it for emphasis. Right. You integrate x squared with respect to x, you get 1/3 x squared. Now be careful, we are integrating here. If you integrate 5, don't you get 5x? If you integrate 12, you get 12x. If you integrate y squared, you get y squared x. Do you see that y squared is being treated as a constant? Does that make sense? That you're just integrating with respect to x in the same kind of rules that you used when you were integrating with respect to y. Now what you then do is you say, okay, I'm going to evaluate it from x equals -1 to x equals 1. I mean, just like you usually do, right? Find antiderivatives and then evaluate at these two numbers. So I now have the integral from -1 to 1. So let's see. I'll keep my little dotted box going for a little while longer. Well, what's it going to be? Plug in 1, you get a third. Plug in 1 here, you get y squared. Take away, plug in -1, you get a third. Plug in -1, you get -y squared. Then, well, you've got a third, take away a third, they're gone. You've got a y squared, take away a negative is plus. So what you're now left with is 2y squared dy. And so we've integrated with respect to x, and we now have 2y squared. Now, that guy now gets integrated with respect to y. Do you see, we've kind of, it's like unpeeling an onion, right? We've taken one layer away, and we've got one more layer to go, right? Now, this one's a little bit easier to do because isn't this kind of calc 2? It's just got one variable, y, and you're integrating. So what you're going to get is add 1 to the power, divide by the new power, evaluate that at -1 and 1, and that should get me 2/3 times 1, take away 2/3 times -1, and just enough room to squeeze it in. The answer is 4/3. So there is our first double integral. The double integral of this function using this rectangle at the floor. So far, so good. Now, if you're trying to imagine what on earth have you found, like what is this number 4/3, right? Because it will be a number. Double integrals, as long as the limits of integration are numbers, right, will be a single scalar number. Well, I'm going to try my hands because there's no other way to do this. Can you imagine this rectangle on the floor, and above you, you've got this x squared plus y squared surface. If you build walls all the way up till it hits that curve, right? Can you see what you would make would be a rectangular cuboid with a circular kind of cup shape cut out of it? So what you're actually doing is finding the volume of a shape that would look something like this, and this is not even vaguely going to work, but it's the best I can do in the world, right? Can you imagine that would be the rectangle, but when it hits the surface, there's a kind of curved bowl thing going on. If you ever smoked, have you ever seen an ashtray that had a hollow ball-like bit cut out of it? The 4/3 is the volume of that ashtray. So that's what you're getting when you find a double integral. You're getting the area of the solid that you would get if you took the rectangular area and went vertically upwards and met the surface, right? And imagine you cut off the rest because it doesn't matter. And whatever is inside, right, that shape, that's what you've just found. So that's if you're a visual person, that's the best I can give you. If you're an algebraic person, hey, it's a process, right? You integrate with respect to x, then you integrate with respect to y. So let's talk about properties that double integrals can have. Suppose I have a double integral over some region, and I'll call it R. Some rectangle R. And the function's called xy, right, as they all are. And the one I've just did here is dx by dy. So I guess in my question here, that guy was 4/3, right? if you use the same rectangle and you use the same function, but you decide to do it in that order, so you integrate with respect to y first, and then after you've got that answer, integrate with respect to x. What do you think the second answer is going to be?
4/3.
Yeah. Which is quite helpful, because what it says is, if you're doing a double integral with respect to x and y, and it doesn't matter if you do x first or y first, as long as you do both of them one after the other, the answer to the double integral will be the same number. Sometimes that can be helpful. Can you imagine you've got a really ugly function f of xy? But if you integrate with respect to x first and then with y, it's a little bit less ugly than if you switch the order. The analogy might be, can you remember doing differentiation of some functions and it would be easier to do the second derivative y first, x second, rather than x first and y second, right? Clairaut's theorem, essentially. Okay, so you can imagine there may be some situations where that would be of benefit. It is a nice property for a function to have. So next then, let's do some more practice at more complicated functions and double integrals. So let's suppose I have a function f of xy, and this time it's x plus y over x squared plus 1. And I want to integrate it between x equals 0 and 1 and y 0 and 2. Now, if you set up this integral, it will be a double integral. X can go from 0 to 1, and y can go 0 to 2, and the function goes here. We're going to do a dx first and a dy second. Are you comfortable about the order that the limits of integration are and how they match the x's and the y's? That does matter. You know how 0, 1 and 0, 2 are not the same. Now, if you wanted to do it in a slightly different order, the function does not change. But did you notice that the limits of integration, excuse me, did you notice that the limits of integration follow the variable? So can you see that when it was x first, it went x from 0 to 1, but when it was y first, y went from 0 to 2. Do you see that there is a distinct difference? Because I don't want you to think you just keep these the same and you can switch the x's and y's and it won't make a difference, right? That's part of the process. Now that you can see these two equations, do you think I should go for x first or y first? I have two choices, after all. Silence is deafening. Anybody? What do you think? Is there any difference? Do you think they're both equally ugly so it doesn't matter? Or do you think you may want to do the x first, or do you think you may want to do the y first?
Y first?
Okay, so let's choose this one. 0, 1, 0, 2, this function. Now, if that was me, I would have chosen y first as well. Now, that might have been a lucky guess. Has anybody got any suggestions why you think this might be easier to do with respect to y first?
You avoid the quotient rule?
You do right now, at least, right? But you don't have a quotient rule integration, but it'll be a use of, but you avoid it anyway. Now, we got to figure out what on earth this guy looks like. I'm going to put my little invisible dotted line thing. Right, that's essentially the first guy, right? So I'm just going to take this out and figure out what he is, and then once I get the answer, I'll return here and put the answer in there. And that way I don't have to keep writing all this stuff at the ends over and over again. So, a little wall to separate it. I need to find the integral from 0 to 2 of x plus y over x squared plus 1 dy. And I need to figure out how I'm going to tackle this integral. This is like 5 plus y over 26, right? It's really not a very ugly thing to integrate, but it is quite awkward to integrate the way it is written, okay? So I'm going to show you my approach to this question. Do you see that I've pulled out this x squared plus 1 and pulled it out as a fraction, 1 over x squared plus 1? The reason I've chosen to do it that way is that if something's a constant like 5 or 25 or a half, can't you just pull it out of the integral and just stick it at the end and it doesn't matter? And that's a very useful technique when there's x's floating about and you're trying to integrate with respect to y. Because right now that's cluttering the picture. This is much cleaner to do. And because the variable is y and x is a constant, I could do that. I couldn't pull a 1 over y squared plus 1 out if I was integrating with respect to y. That would not work algebraically. So I now have 1 over x squared plus 1. Integrate x with respect to y, you get xy. Integrate y with respect to y, you get half y squared. And you evaluate it at 0 and at 2. So I have 1 over x squared plus 1. Plug in 2, you get 2x plus 2. Subtract nothing. So we are left with 2x plus 2 over x squared plus 1. So this integral now becomes the integral from 0 to 1 of 2x plus 2 over x squared plus 1 dx. Now, if you've done this process correctly, once you've done one of the two integrals, the guy that's left should have nothing but x's in it. And this question here is not a Calc 4 question. This question here is a Calc 2 question. So I'm now going to start on a new piece of paper and figure out what he is. Excuse me. So I need to find the integral from 0 to 1 of 2x add 2 over x squared plus 1 dx. And it's surprising the number of things people are rusty about, because, you know, it depends on how long ago you've done your integration questions. If you've been if it's been a while, then you may forget some of the strategies here. I need to integrate this. I can't really do it in one go. I got to fix it in some way to make it possible. So the first thing I'm going to do is to break it into 2. Okay, so has anybody any ideas why I took this and why I split it this way instead of some other approach? Okay. Right now, I have a fraction 2x plus 2 over x squared plus 1. There are no real strategies. If I tried to do a u-sub on that question, the way it's written here, I would get bits left over that I couldn't handle, and the u-sub would disappear. Now that I've got it in these two parts, this fella here, he can be integrated. What is the integral, the antiderivative, of 2 over x squared plus 1? Two over
Inverse
x.
tan x.
Right, and since there's two of them, 2 inverse tans. Let's finish this off then. That means 2 inverse tans of 1, take away 2 inverse tans of 0. The inverse tangent of 1 is pi upon 4, which you should all know. And the inverse tan of 0 is 0. So this ends up being pi upon 2. So this piece is pi upon 2. Okay, I now need to figure out what to do with this integral. And it's not going to be anywhere as clean as the other one. 2x on the top, x squared plus 1 on the bottom. There's a method that we can use to do that.
Natural logarithm?
Not yet. There will be a natural log eventually, but we have to do something to get there. There's a method used for doing questions like this. It's called u-subs. That's what I was looking for. So I have 2x on the top. That's the one. Now, some people do it as a UV method, which is fine. I do it this way. So we have an integral, we have a 2x, we have an over u, we have a 1 over 2x du. That becomes the integral of 1 over u du, which becomes the natural log that you were talking about. So maybe you just saw the whole thing in one go, which becomes, if you return it back to its original, that fella evaluated at 0 and evaluated at 1. So you get the log of 1 squared plus 1 is 2. Take away the log of 1. The log of 2 exists, that's 0. And there is your final answer. So in this case, the double integral had a value of log 2 plus pi upon 2. What's kind of nice about that question is that it shows you that although you're integrating 2 times, it's a lot harder than it would have been in the Calc 2 world. First, you have to remember, you know, that the first integral, at least one of the terms is going to be considered a constant, so that kind of adds its own little degree of difficulty. And then the second process, that once you've done that, you still have to know all the usual u-subs, x-subs, power rules, even as simple as, do you know what the integral of secant squared x is? Something like that.
10.
Fine. Do you know what the integral of 2 to the power of x is?
Isn't it natural log 2 to the x?
Okay, so
natural log x? Or?
No, you were right with the 2 to the x part, so keep that, Jackson, right? The natural log of 2 is part of it as well, right? Okay, now little things like that, you just go and look up if you forget it, because they're just memory things. But then you have u-subs that we've just done. And do you know there's a technique called integration by parts? Can you remember that guy? Can you imagine you might get a question where you're trying to integrate x sine x? Right. So be on the lookout for all the techniques in Calc 2 randomly just chucked in at a question. Now, hopefully you're going to get a lot of power rules because they're easy to deal with, and not so many integration by parts or U-subs, but there are always going to be some. So we have to be, we have to be careful. Try another one. Suppose we do the integral from 1 to 2 and the integral from 2 to 4. And this time I'm going to do so, nothing too scary. In this particular question, and I suggest you do this unless there's a big demand for you to, for some reason, change it. If the homework question gives you an order, the chances are that's the best order, so just stick to it. Now, in this story here, we're going to take care of this fella first, right? Now, x squared plus y squared cubed. How am I going to deal with that? Now, I'm not taking this question to the end. I just want to show you the algebra techniques that you sometimes have to employ. This question has got issues, hasn't it? And we have to deal with those issues. So do you know what you're going to have to do here is you're going to have to FOIL this whole thing out. And the answer when you get that is x to the 6 plus 3x to the 4y squared plus 3x squared y to the 4 plus y to the 6. And you just trust me on that. Now, you can then integrate that. So I'll take it one last step. This guy is 1/7 x to the 6. This fella here is 3/5 x to the 5 y squared. This one here is x cubed y to the 4. And the guy at the end is y to the 6 x. And you're going to evaluate from x equals 2 to x equals 4, and pretty much you're done. Now I'm making one change here. I've changed the x squared plus y squared to just being x plus y. Right. So this isn't finished. I just took it to that point. This is the one we had the first time. This is the guy we're having the second time. The first method would be exactly the same as the other one. Just FOIL the damn thing out. There is another way of doing it. Suppose you want to integrate x plus y brackets all cubed. So you want to integrate x plus y in brackets all cubed. There is another way of coming up with that same answer. Suppose that was x plus 2 brackets all cubed, right? Could be that. Wouldn't you just do a version of the power rule? You'd add 1 to the power and you divide by the new power. You can then evaluate this at x equals 2 to x equals 4, and you're done. right? X plus 2 brackets cubed, is it not x plus 2 to the power of 4 times 1/4? If that x had been 4x or 2x, wouldn't you then finish with a times a half or times a quarter? And that would be it. So if you can see shortcuts, to me, that's much easier to do, because first, I happen to know what that is, but you would probably have to do it the hard way, right? And then I still have to integrate it, right? I haven't finished. Still have to integrate. And then I have to plug in x is 1 and x is 2. Whereas in this format here, it's much cleaner and easier to do. So the moral of the story is to always be on the lookout for shortcuts to how to do a particular integral. Oh, I should keep that there. I'm going to move to the book now, or the software. And so you hold on for a few moments, and we'll look at some of their questions just to get a feel of how they are phrased and what you're expected to do. And we may have some people who have got some homework questions, and I could use them as examples. So while I'm getting this set up, okay, I think I'm ready. Here we go. Okay, this is us inside 15.1, integration over rectangular regions. If someone has got a question they'd like me to do, then I'll do that. Otherwise, I'll just pick one at random and show you what it's like. If anybody has done any of these 20 and they'd like to see...
You do 6.
Okay, good candidate. Here goes. This will be my version of 6. This fella here, right? Or something very similar. Okay, when I'm finished, the answer better look like that. So, oh, that reminds me, when I was checking over working, and some of the reasons the computer was giving you 0 points or not getting it correct is that the books, at least for tests, is not generous about the decimal version of an answer. Right? So if the right answer was 4 pi, it wanted 4 pi. It didn't want 4 times 3.14 or whatever that is as a decimal. So we'll bear that in mind for next time. So here we go. I want to get the integral from 0 to 3. I'll get this back on my screen in a minute. I have a 9xy, and then there's a square root of x squared plus y squared, finishing with the dy and the dx. So they want us to do what, y first and x second. I can handle that. Stop the sharing. Are you looking at the big version of the screen again, or will I have to do something to get that back? Big version? Okay,
Yeah, I can see the screen.
Good. Now, let's worry about just that. And then once I'll come back to the other stuff. So, if you want to find the integral of 0 to 1 of 9xy, the square root of x squared plus y squared dy, you have to think of x as being a number. So let's pretend it's 1. So it's 9y, the square root of 1 plus y squared. Right, that's what I'm looking at. So now we have to figure out what technique you would use in a question where the x was like a number 1. What method would I use to solve 9x square root of x, 9y square root of 1 plus y squared?
Would you use u sub?
I would. Now, in this case, wouldn't the u sub be whatever is inside there? Right. So it's u sub, and the u sub is what's inside the square root. This is different from Calc 2. X squared is considered a constant here, right? It's like 1 or 21, right? So when you do the du by dx. At least that's the way I do. The variable I want is y, so technically I need to do du by dy. If I'm being really nitpicky about it, it's actually the partial derivative I'm doing. In this case, with respect to y, doesn't x squared get you nothing? So all you get is 2y. And so du is 2y dy, and 1 over 2y du gets me a dy. And that's how I set up my u sub questions. So this now becomes the integral of 9xy, the square root of u, and 1 over 2y du. So I now have, cancel out the y's, I have 9 over 2x, the square root of u, du. Are we cool so far? Right. Anything that is a number or a variable that's considered a number, it's probably a good idea in these questions just to stick them outside. Just get them out of the way, because if you keep them inside, the temptation is to do stuff to them that you're not meant to. Now, basically, this fella here is a half power. Great. So I would add 1 to the power, and I'd divide by the new power. And then I could turn this guy into the square root of u cubed. I'm maybe putting in more lines than you need. That's 2/3. And I'm now going to return it to that format. So I am going to get this fella, it's going to be, well, I should tidy this up a little bit. The 3's cancel, the 2's cancel. So it looks like what you get is 3x, the square root of x squared plus y squared, right? So what I'm going to do is 3x, the square root of x squared plus y squared, evaluated at y equals 0 to y equals 1. And you plug in y equals 1, you get 3x, the square root of x squared plus 1. If you plug in 0, you get take away 3x, the square root of x squared. I wish that wasn't there. So I now have 3x, the square root of x squared plus 1. Would you agree that the square root of x squared can be considered to be x? So that's really x times 3x, so it's take away 3x squared.
Did you take the, shouldn't the x squared plus y squared be cubed?
Oh, correct. Which is going to make x to the 6. Square root of x to 6 is x to 3. Thank you for catching that. So it's 3x, the square root of x squared plus 1 cubed, which I'm happy about. I'll do a double take on this one. If you plug in the answer 0, you get x squared, but x squared cubed is x to the 6. Square root of x to the 6 is x to the 3. You've already got an x. So it looks like we've got that guy. Now, that is a lot of working, and we're only halfway there. So to kind of tell you where we are, our original question looks something like this. We took this piece here, and we found out it was integral from 0 to 3. And we have a 3x, the square root of x squared plus 1 all cubed. Take away 3x to the 4 dx. Okay, so one integration out of 2 is over with. Do you see that everything here has x's or numbers, so that's a good sign? So let's keep going. I want to integrate this piece and I want to integrate this piece. I would separate them out. This one here I can do pretty easily. It's just a simple power rule. Evaluated at x equals 0 to x equals 3. Good grief. 3, 9, 27, 81, 243, 723. Don't quote me on that. Well, that's what I believe it is. Okay, how are we going to tackle this ugly mess? Three x square root of x squared plus 1 cubed. Interesting. We've done a technique that was a simpler version of this today. It was just an x squared plus 1 on its own inside the square root. Can you remember that one was a use-up? So is this one. I'm going to do a use-up of x squared plus 1. You're going to get the integral of 3x, the square root of u cubed, 1 over 2x du. The x's cancel, so you're now going to have 3 over 2. Do you know the square root of u cubed is 3/2? Which means that I can add 1 to its power and divide by the new power, which is cancelling to give me 3/5. That fella becomes that. That fella becomes that. Evaluated at x equals 0 and x equals 3.
When did the y squared become the 1?
When did the y squared become the 1? When we were at this line here, y is 0 and y is 1.
Oh, okay.
It became here, it became a 1.
Okay, I see now.
Now, in this case then, I'm going to have 3/5, the square root of 10 to the power of 5, take away 3/5, square root of 1 is 1. So according to my answer, it should be 3/5, 10 to the power of 5/2, take away 1. And I'm going to zoom back here. And if it's not right, it's because I can't count.
You didn't. I don't think you included the. There's the other part.
Oh, that piece.
The 7.
Right. So 723 fifths. So 726, I think. Okay. Just going to zoom in, see how close I got. Okay, I'm going to put this on the screen and show you something that's really annoying. Yes, that's the word. This is the answer they've got, and this is the answer I have. And the thing that's bugging me most is, Do you know I had a 3 and they have a 6? If you take the 2 out of this thing and bring it back inside, so you have a 3/5, doesn't 2 times 5 get you 10? And doesn't 10 times 10 to the 3 halves give you 10 to the 5 halves? So there's where that guy came from. The number they've got is 244. So I suspect that if you go back and look at my working, I probably screwed up in one of the calculations, because I have 726 and they're going to have 244. So pretty comfortable I got it correct, apart from some arithmetic mistake somewhere in the middle. But something that takes 2 pages, it's not hard, especially when I'm toing and froing with my brain to screw it up. This is the bit that bugs me. That, to me, seems a very weird way of splitting up the answer. Do you see the 2, the 6 and the 5 here? I'm saying if you bring out a 2, you leave 3/5 behind, which is what I had. 2 times 5 gets you 10. 10 times that guy gets you the 5 halves, so I got the 5 halves bit right. And doubling that gets you 244. So if you can figure out how 726 should have been 244, I've nailed it. And unfortunately, that is the end of today, apart from Natalie, who's going to hang around for a few more minutes so we can fix something out for her. And I'll see you all.
I had a quick question.
Sure, go for it.
I got an email saying that there was like a test was going to be visible on like WebAssign, but whenever I go there, like all that's there is just like the current assignments.
Yeah, it was a ghost email. It's some weird email from 4 days ago that finally gets sent.
Oh no! Okay.
The only email that you should have got that you should be paying any attention to is one that I sent this morning, although I don't know when it arrived with you. And that's the one that gave you your test grade, and it talked a little bit about the Zoom meetings and the sections that we're doing this week. So that's the only email you should really pay any attention to. So if I don't know what you receive, but if you receive, hey, test 1's about to start.
Okay, so it just came late.
Ignore it, because
okay.
It was correct when I sent it. It wasn't correct by the time it arrived. So
okay, that makes sense.
Something weird is happening there. Hopefully it won't happen too often. So I'm going to say goodbye to the rest. So Matthew, Dom, Alan, I need just a few minutes with Natalie, and then we're out of here. There we go. Almost gone.
Have a good one.
All right, thank you.
You're welcome. If you get stuck on anything, you know the usual, shoot me an email. It's probably going to have to be done by Zoom. You can imagine the amount of writing on this. I already have some examples online. Yes. So I think I put them under the section that is something like web homework, although technically they're not homework questions, they're just worked examples. So if you need some more practice at looking over the algebra of these things, you could go there. And there's some other things floating about. I'm going to add some YouTube videos. If anybody comes across some good ones that are the ones that I like tend to be too long. So if you could say, hey, this is a good 10-minute one and I found it very helpful, if you can shoot me the address of it, I can add it to our list so other people can use it as well. Okay, well, bye-bye, guys. Come on, Matthew, Dom, and bye-bye, Matthew. Okay, hold on a second, Natalie. I'm going to check your grade, and we'll see what we can do to make it fair so that you get the same time as everyone else. So I think I click on this view.
Was I the first one to take the test then? Like, did you fix it after I took it? Or
Yes, I fixed it after you took it. But virtually the minute you mentioned it, I went and fixed it. So I don't know if you went back any time quicker than that.
No, I was waiting for an email back to see if
Yeah, at that point in time, it was putting out fires. So let's check your test.
Also, I don't know how